MBCP technology uses specific biphasic chemical structure. Providing a stable environment favoring cell adhesion and osteoconduction, hydroxyapatite is combined with the highly soluble tricalcium phosphate to promote bioactivity through the liberation of calcium and phosphate ions. The specific structure of MBCP consists of micropores, with microscopic crystals absorbing biological fluids and local growth factors while increasing permeability, and macropores, enabling cellular colonization, neovascularization, and newborn formation. MBCP is synthetic and fully resorbable. MBCP is available in chips, shapes, and injectable paste form. Specific delivery systems are used to facilitate implantation. Immediately post-implantation, biological fluids, blood, localized growth factors, non-collagen proteins diffuse in the network of micropores and macropores. Simultaneously, colonization commences, first with macrophages as part of the healing process. These macrophages nest in the micropores and secrete growth factors promoting healing and osteogenesis as they begin to absorb and resorb the bioceramic. The interaction with biological fluids and the macrophagic resorption activity combine with the dissolving properties of tricalcium phosphate to saturate the micropores with phosphate and calcium ions, which in turn induces the formation of biological crystals resembling natural bone and locally integrating proteins and growth factors. Stem cells begin adhering to the newly created interface of biological crystals and gradually differentiate into osteogenetic cells, osteoclasts for resorption, and osteoblasts for bone formation. This process of osteoconduction and osteogenesis is also referred to as passive osteoinduction. As they adhere to the surface, osteoclasts progressively resorb the biomaterial, liberating ions and growth factors previously absorbed during the bone crystallization phase. This is an important bioactive phase behind MBCP technology. Osteoblasts from bone marrow and stem cells migrate to the surface freshly remodeled by osteoclasts. Stimulated by local growth factors and ionic release, they begin synthesizing the extracellular matrix by depositing a combination of collagen fibers and non-collagen proteins that are both osteostimulating and osteoconductive. Intercellular communications are promoted, calcium and phosphate ions are absorbed and participate to the mineralization of the newly formed matrix. At the same time, new blood vessels are formed to nourish the newly formed bone. Progressively integrated within the mineralized matrix, osteoblasts mature into osteocytes, thus participating to the reconstruction of the overall bone architecture. The new bone increasingly becomes lamellar, filled with collagen fibers and blood vessels, gradually replacing the synthetic matrix and acquiring the properties of natural bone. A few months into the process, bone remodeling progresses, promoted by mechanical constraints unique to each implantation site. As part of this process, more and more synthetic biomaterial is resorbed until eventually it is completely replaced by natural bone. MBCP-based bone matrices are an ideal substitute to autografts and allografts in the treatment of bone defects in orthopedic and maxillofacial surgery.